Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat feature. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these tech talks have been designed to share straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that a custom manufacturer such as Quantic TRM adds. To begin today's session, I'm happy to once again introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with the company since the early 90s, and his passion for helping to resolve customer problems has only grown from year to year. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. Happy to. Really, what we're going to talk about today are high-frequency components, and really, what does it mean for a high-frequency component, and how does that affect, really, from a design standpoint and from a manufacturing standpoint, really, what impact does that have going to these higher and higher frequencies? And then we'll go ahead, we'll talk about some Quantic TRM differentiators, and then we'll wrap it up with a summary.
Okay, well, that sounds good. And so to start, how do we define high frequency?
High frequency is kind of a vague term, right? It's one of those things where it's, what's high to you is not necessarily high to me. And I think historically, I think that's really, really what is a good way to look at this. If you look back in the 1930s, high frequency was, UHF, which at this point is very low frequencies. So as time goes by, that line of where high frequency really starts really keeps on changing. And really, I think if you look at it with today's terms, we're really looking at Ka band and above, which is 26 gigahertz. Really is kind of the new high frequency. I know when I first got into this industry, X band was a high frequency. It's not quite so high anymore. And really, I think if you take a look at Quantic's portfolio of what we have for power dividers, combiners, directional couplers, and hybrids, we cover a lot of the high frequency sort of applications as we're going ahead and designing these products. So it's an interesting sort of topic to go through and see really what stretches do we need to do to have to continue to work in this field.
Okay, now I've also heard you say that high frequency brings about a number of technology design challenges. Can you explain?
Sure. And what I'll say here is, going back to my initial comment with the 1930s, a lot of that technology that was done there was based on wire-wound transformers. It was before we had distributed technology to even be able to build products like that. What happens now as we move up into Ka band and above is that there's another step function that needs to happen. We can still use distributed technology. However, we have to be careful now about making sure that the line lengths that we have look like transmission lines and don't look like lumped elements. Those are things like the wavelength to physical the wavelength to physical length of the transmission line ratio. As the quarter wavelengths get shorter and shorter and shorter, the width of that line now becomes an appreciable proportion of the wavelength. And then those transmission lines no longer start behaving like transmission lines. They start behaving like lumped elements, which is really a major hurdle to overcome. One way to get over that, of course, is to go through there and start working now with different geometries and different stack-ups of the PCBs to make the line widths thinner, and therefore we can maintain those sort of length-to-width ratios. There are other things we can do there as far as circuit design approaches are concerned. We can now, instead of working with stepped impedance transformers where that quarter wavelength really starts becoming critical, we can go in there now and start looking at high pass structures as opposed to band pass structures. And by building things like that, we can now go ahead and get away from that line width to line length ratio in yet another way. A lot of these high pass structures really, from a physical standpoint, aren't practical down at lower frequencies because the structure needs to be an appreciable length of a wavelength long, which makes these structures really too large for lower frequencies. But when you get up to higher frequencies now, as the wavelength gets shorter and shorter, it just makes sense to go on in there and start building that way. Moving over into some physical geometries, there are a lot of things that we do as we interconnect between sections now, where the parasitic of that step function now becomes critical. And that moves us over now into some parasitics that we have to deal with. Really, what we need to do now is we need to start thinking about band all pass networks and band and high pass sort of networks, as opposed to a band pass sort of structure. Parasitic effects, once you get up to higher frequency, are harder and harder to tune out. And as such, we need to make sure that we're very careful to actually have these designs so we don't actually have these parasitics to begin with. So we have to pay careful attention now to make sure that what we have is a quote unquote better transmission line running through here to make sure that we don't have these sorts of transitions. Another thing we have to look at now is suppression of unwanted modes. As the frequency gets higher and the wavelength gets shorter and shorter and shorter, extra space around the circuit is an invitation for a higher order mode to begin to propagate and begin to have problems. So things like PCB stack ups, board spacing, the overall thickness of the PCB stack up between layers of the active layer, the via layout of what we have for the ground structure, the spacing between the vias, all these sorts of things really play into suppressing unwanted modes. And the higher and higher frequency you go, the more critical these things become.
Well, based on that, should we conclude that there are also manufacturing design challenges related to high frequency components?
Absolutely, and just like from a design standpoint, where we have to deal with precision and making sure that we and precision in the fact relative to a wavelength, I think is probably a good way to think about it, because as the wavelength gets shorter and shorter and shorter, what is a perfectly acceptable level of detuning due to a manufacturing variance now becomes a very appreciable proportion of wavelength, in which case then that can cause some major issues with yield. So part of what we're looking at doing now as we move up higher and higher in frequency is to try to move into a manufacturing process which is more machine-based, and therefore removing the human variation of assembly and manufacture. So as parts get smaller and smaller and smaller, we're going to rely more and more on machine-based manufacturing to make sure that we can have a repeatable circuit and a repeatable interconnect between sections, as well as other vias that are in play. Also, manufacturing tolerances really become a much more critical item. And sometimes now we have to begin to moving into other fabrication methodologies in order to make sure that we can maintain tolerances. I think the good news here is the fact that some of these tighter manufacturing tolerances, they do limit the size of the board that you can work on. But then again, the circuits are getting smaller and smaller. So therefore, the ratios kind of work out okay. So we can go in there now and start using some different manufacturing technologies to get tighter and tighter tolerances that are required, basically just to maintain the same sort of variability of performance that we have at lower frequency, sub 20 gigahertz sort of performance, moving up into Ka and above. Also as you get into higher precision equipment, the equipment does cost more. So this is something that we have to be cognizant of as we're going through there as well. Whether it's test equipment or manufacturing equipment, the price does go up as you go higher and higher in frequency.
Well, excellent information as usual. How would you summarize then?
Yeah, so basically, high frequency technology that we're currently using it's the next stepping stone to the advent of distributed technology and strip line technology that was developed many years ago. Really, what it comes down to is going in there and trying to manage the parasitic effects of the step discontinuities between sections, between the inputs and outputs of the circuits. Also, going in there and now taking a look at how we are going to be designing the circuits. Not all circuits are going to be bandpass structures, moving into some high pass structures as well, and using some different circuit topologies that will allow us to control and reduce the amount of parasitics that we have in the overall circuit design. Also, I'm going through there and making sure that we have some very good control over the propagation modes, making sure that the stack up is manageable, to make sure that we don't generate higher order modes as we're going through the construction, whether it be via spacing or the size or the thickness of the substrate that we're putting the circuit on. These are all very important things we need to consider as we're moving up higher and higher in frequency, and they will dictate very often the way we approach the circuit design. Something else really that we need to take a look at is the characterization of calibration of fixturing. Very often there are some subtle things that go on measuring lower frequency components with calibration and accuracy of data. And as the wavelength gets shorter and shorter, those errors become more and more significant. So we need to be very cognizant of these sorts of errors as they come up with calibration. Because now those errors are now becoming significant as we go higher and higher in frequencies. So we have to make sure that we are going in through there and actually making sure that we have the best calibration methods possible, always using them and making sure that the data we're getting is the most accurate.
Okay, and finally, what's different about the way Quantic TRM deals with, well, these kind of products and any of the components, really, for that matter? What are the differentiators?
Sure. So Quantic TRM really, I think, as our main differentiator here is we want to work with our customers to make sure that the product that we deliver is indeed the product that they need. This is actually a very important piece for us to make sure that the product that the customer ends up with really is indeed what it is that they need. And this is going through and having that discussion with them to go through and actually make sure that all of the subtle things that that happen as part of the design and part of the implementation into the system, make sure all these things are addressed. So we like to go through there and make sure that really the product that we're delivering is indeed the best solution for the customer. We do that through whether it's through the environment that these are needing, and whether it is the testing that they need to be done in, or whether it is indeed a specific packaging requirement that they need. We want to make sure that the product that we deliver is indeed what they need. Also, we like to think of ourselves as a solution provider or as an extension of our customers' engineering team. So we like to work with them to make sure that really all those things are looked at in great detail to make sure that the product that they end up with is indeed the best product that they need.
Okay, and we do have a question, which is, you had talked about calibration and fixtures at high, and are the high frequency parts limited to any specific technology like connectors or surface mounts?
That's a good question. Connectors at some point do stop operating. I mean, everything has a limit. So we have to make sure now that the connectors that we're looking at really do meet the requirements. Your standard SMA connector does not work above 26 gigahertz. So we have to make sure that if we're going higher and higher in frequency, that we're not using those sorts of connectors. Surface mount, on the other hand, theoretically doesn't have those limits as long as the interface is designed properly. So going through there and working that interface out and modeling that interface at higher frequencies is extremely critical. And it's one of those details we need to make sure that is addressed as we're going through the design. Something else also to consider about as far as that interface is how we're going to test for that interface. Testing for a surface mount interface at very high frequencies requires special tooling because we're not soldering the part down to test it. We have to be able to make that connection and have that contact so we can measure and take that data without having actually any damage or putting solder on the part. So that is something that we really need to go in there and really make sure that is indeed working properly, and that is a detail that we need to work out ahead of time. And it's a very important detail to consider.
Okay. Well, thank you, Shaun. And thanks again to all of you for joining us. In conclusion, I think the bullets on your screen say it all. And going forward, if you are a customer and have more questions, please feel free to call our engineering hotline. The number is on your screen, 888-677-6877. Obviously, there are no costs associated with these conversations, and we'd love to hear from you. If you're one of our field sales representatives, then of course, your calls are always welcome too. And looking ahead, the next Tech Talk will be on Tuesday, June 20th at 1 p.m. Eastern, and the topic will be surface mount products. Thanks to all once again. Thank you, Shaun.
Thank you, Paul.